The first paper is How do recommendation model amplify popularity bias? An analysis from the spectral perspective. Let's start with the context. We know that interaction data is recommendation system typically follow a long-tail distribution, meaning a small number of popular items account for the vast majority of interaction. The problem is that when models are trained on this data, they tend to inherit or even amplify this bias. This results in recommendation lists being dominated by popular items, while long-tail items are ignored. The core contribution of this paper is explaining why this happened from a spectral perspective. The author presents two core insights. The first is the memorization effect. Through singular value decomposition (SVD), the author discovered that item popularity information is actually memorized in the principal spectrum of the predict matrix. Specifically, the principal singular vector aligns almost perfectly with the item popularity vector, with a cosine similarity exceeding 0.98. The second insight is the amplification effect. This is the most fascinating part. The author points out that the real mechanical cause of bias amplification is dimension reduction. Because the embeddings we use are typically low rank, combined with the dynamic of gradient descent, the model prioritizes learning the principal component. This cuts the weight of the principal singular value, which present popularity, to be disproportionately amplified, thereby suppressing other signals that represent true user preference. Okay, based on this finding, the author proposed RESN, regulation with spectral norm. This is a plugin method. The principle is intuitive, since popularity is hiding in the principal singular value. We simply add a regulator to the loss function that specifically penalizes the magnitude of the principal singular value. The author also developed an efficient algorithm that exploits spectrum property to avoid expensive full SVD calculation, making it highly efficient. And regarding novelty, this paper breaks away from the traditional curse-grave analysis framework. It is the first study to analyze the bias problem from spectrum theory, identifying dimension reduction as the mechanical cause of bias amplification. This is a very novel perspective with clear physical meaning. In terms of soundness, the paper provides rigorous mathematical proof and validate the effect across 7 real-world datasets. Regarding significance, popularity bias is a common issue in the recommender system. RESN provides a simple, model-agnostic, and efficient solution that holds high practical value for both academia and industry. However, the paper does have some weakness. First is static analysis. It only analyzes the static matrix, ignoring how bias evolve over time within the dynamic feedback loop of the recommender system. Second, the theoretical derivation is primarily based on matrix factorization and MSE BPR loss. For mainstream deep nonlinear model, the explanatory power of this linear spectral theory might decrease. This leads to opportunity for improvement. Future research could attempt to extend spectral analysis to temporal model or validate the theory's applicability under more complex deep learning architecture. And finally, for this paper, we would like to ask the 3 questions. And the first is, this spectral theory is based on linear decomposition. How can it be applied to non-linear deep model where SVD cannot be directly performed? And the second is popularity sometimes signal high quality. Thus, RESN indiscriminately supplies high-quality popular item, potentially hurting recommendation quality. And the third question is in online learning scenario where data distribution shifts rapidly, so spectrum recognition still effective, or does it require dynamic adjustment? Okay, next we move to a second paper. A cost-effective framework to evaluate LLM generate relevance judgment. The background is simple. In information retrieval, we need annotate data to evaluate search engine. Human annotation is expensive, while LLM annotation is cheap but prone to error. Current practice validate LLMs using historical dataset, but this doesn't guarantee the LLM's performance on brand new data. Okay, in this paper, propose a statistical framework aimed at verifying LLM annotation quality with minimal human involvement. The other design two procedure, the confidence base. You set the desired confidence, and the framework tell you how many sample human need to review, or the budget base. You set your budget like 100, and the framework told you the margin of error for the evaluation result under this budget. And regarding the novelty, the highlight is that it doesn't rely on historical data, but directly validate the current unseen data. It shifts the problem from simply ranking evaluation to statistical estimation of annotation quality. And soundness, the paper's statistical foundation is solid in employ simple random sampling and word confidence interval. Ensure that the estimates are unbiased. The other also validate its effectiveness on multiple TREC datasets. Okay, regarding significance, the contribution is substantial. Experiments show that it requires only 6% to 16% of human effort to achieve a 95 confidence level, significantly lower the barrier for creating new datasets, align with the green IR trend, and provide a reliability budget for future AI-generated datasets. The weakness of this paper is relied on the simple random sampling, the SRS, in highly imbalanced dataset. SRS might fail to capture any positive example, causing the estimation to fail. Additionally, word interval can be unstable when the sample size is very small, like smaller than 13. The current framework is also limited to document ranking tasks and has not yet been extended to generative tasks. And opportunity for improvement include introducing more advanced simple methods, such as stratified sampling, where layering based on querying difficulty might be more efficient. Furthermore, combining this with active learning could focus human intervention on the most uncertain sample. Okay, finally, for this paper, we propose the following three questions. And the first is, the paper mentioned the stratified sampling is challenging. Based on experiments, which stratification criteria will be most effective in reducing variance? And the second question, how does the framework differentiate between valid disagreement and LLM hallucination if human evaluators themselves disagree on a query? Is the framework evaluation still accurate? And the third question, for difficult text where agreement between human and LLM is extremely low, Is the initial sample size of 30 sufficiently robust?
Our group third paper is exploring adapter-based transfer learning for recommender systems, empirical study and practical insights. The core objective here is to investigate if adapter-based techniques can make TransRec more parameter efficient without sacrificing performance. TransRec is a framework that uses raw modality feature like text and image to recommend items and transfer knowledge across domains. Let's look at the motivation. As the figure shows, in large industrial platforms, we typically have a main recommendation channel and various vertical channels, such as sports or fashion, education. The traditional approach requires maintaining a full copy of the fine-tuned model for every single channel. This leads to three major issues. First, parameter inefficiency. Standard fine-tuning updates the entire pre-trained model, leading to redundancy. Second, high storage cost. A separate model copy is required for every downstream channel. The last issue is computation expense. Fine-tuning large modality encoders is computationally expensive and often impractical. To solve this, the authors propose adapter tuning. The idea is simple but effective. As we can see the figure, instead of retraining the whole model, they freeze the massive pre-trained modality encoder. Then, they inject tiny trainable adapter modules into the transformer layers. During training, only these small adapters are updated, which drastically cut down storage and computational costs. Moving to the results, the study showed that TransRec with the state-of-the-art adapter tuning achieved performance comparable to full fine-tuning. However, there is a trade-off. While it is highly efficient for textual content, they observed a slight performance drop when applied to visual item recommendations. In summary, the paper's main strength is that the first comprehensive empirical study systematically investigating adapter-based learning for TransRec. On the downside, the paper focused more on empirical insight rather than proposing a fundamentally new adapter architecture. Specifically for recommendation systems. But it opened up opportunity to research to include more diverse recommendation scenarios or complex multi-model combination to reinforce the university of the findings. Here are the three questions about the paper. I want to ask them. First, how do authors expect adapter-based methods to perform on other data modalities, such as audio or graph-based recommendations? Second, does inserting adapter layers introduce any noticeable latency during the online inference phase compared to standard fine-tuning? The last one is based on the study. What's the specific characteristics should a recommendation trailer adapter have compared to standard adapter from NLP or CV. So now let's move on to our group fourth paper, Large Language Model Simulator for CoStar Recommendation. This paper addresses the CoStar problem, specifically focusing on how to recommend newly released items that have no historical interaction data. So let me explain what is warm item and cold item in recommendation system first. Warm item is existing item with rich historical user interaction data, such as click or purchase, allowing the system to learn accurate behavior preference. The cold item is newly released item with no historical data, forcing the system to rely solely on content features, such as description or image, for recommendation. So let's move to the motivation. Existing methods usually try to map item content to user preference, as the figure shows. However, the author identified a critical issue called the content behavior gap. Simply put, embedding derived from content often fail to capture actual user interaction patterns because they mix disparate content and behavior spaces, limiting recommendation accuracy. To bridging the gap, the author proposed Code LLM. The figure shows the framework of Code LLM. Which feature a unique LLM simulator. This simulator uses LLM to generate synthetic user interaction for code item, effectively mimicking how users would react to them. To make this scale for billions of users, they introduced a couple kernel framework. This framework has two stages. So the first stage is filtering simulation. First, it extracts content feature to quickly narrow down the search space from billion to just hundreds of candidates. The method is extract item content using LLMs and map this feature into a filtering space for fast top case similarity search. The second stage is called refining simulation. The goal is feed structure prompts into the LLM for the final few candidates. So they will input some prompt to LLM and do some input optimization. They select only relevant historical behavior to form a concise user context, avoiding noise. So the LLM will output generate a binary prediction indicating interaction probability. Then for the the results are in real world A/B testing. Code LLM consistently outperform all baselines. Specifically, it shows significant improvement in metrics like recall and NDCG compared to traditional method. The key strength of the Code LLM is its ability to use synthetic data to bridge the content behavior gap. But on the downside, a major weakness is latency. Even with the funnel filtering, the final refined stage requires running expensive LLM inference, which can be challenging during peak traffic. This leads to future opportunity. There is a significant potential to distill the LM simulator's reasoning into smaller, faster student model to reduce online computational costs while maintaining simulation accuracy. So, there are the 3 questions about the paper I want to ask. Can this framework be easily adapted to other recommendation domains with different data types, such as news or short videos? Second, what is the specific latency impact of the LM refining stage during high traffic periods in a real-time online environment? The last question is, how sensitive is the performance of the LM simulator to change in the prompt design or the choice of the underlying LM? These are our group paper presentation. Thank you for listening.